Good afternoon. My name is Jaehyuk and I'm a master student at Chun Grade School of Mobility and working in Tukpa Lab. Today I'll presentation my master thesis on driving behavioral response to information delivery system in tunnel driving. So the main focus is VMS and HUD under different luminance and speed limit conditions. The presentation consists of 5 sections: introduction, literature review, methodology, the result, and conclusion. Let me start with the introduction. In this section, I will explain why tunnel safety is important and why information delivery systems are needed in tunnel driving. Road tunnel are important infrastructure, especially in Korea or China, where many areas are mountainous. As shown here, the number and length of tunnel have increased rapidly. However, the main safety concern is not only accident frequency. When an accident occurs in the tunnel, the consequence can be more severe. This is because the tunnel have limited escape space, limited visibility, and difficult emergency access. Also, rear-end collision are common in tunnels, and one accident can lead to secondary crash. So proactive safety management is needed before a risk becomes critical. Then, why is tunnel driving challenging for driver? There are several reasons. First, drivers experience abrupt luminous change when entering the tunnel. This can delay hazard detection. Second, the tunnel interior is visually monotonous. This can reduce vigilance and distort speed perception. Third, a driver needs to process many things at the same time, such as traffic, sign, and lighting, and surround vehicle. Finally, the manual space is limited. So even small delay or error can lead to a collision or a chain reaction. Exceeding tunnel safety measures mainly focus on infrastructure and environmental improvements, such as lighting, visual guidance, and tunnel design, and traffic management. These measures are useful, but they can be costly and difficult to apply to every tunnel. Also, many previous studies focus mainly on single vehicle behavior. However, tunnel risk is not created by one vehicle alone. It is also shaped by spacing, speed adaptation, reaction delay, and the following vehicle's response to the leading vehicle. So this study focuses on tunnel risk as dynamic process. Specifically, I examine how VMS and HUD affect driver behavior and vehicle-to-vehicle interaction stability, and how these effects change under luminance and speed limit condition. So now I will move on to literature review. Previous studies have suggested several approaches to improve the tunnel safety. Lighting improvement and visual guidance can support visual adaptation and speed perception. Information delivery systems such as VMS and HUD can also help driver recognize hazard earlier. However, severe gaps still remain. First, many studies focus mainly on single vehicle behavior. Second, have rarely been compared in the same driving context. Third, luminance and speed limitation conditions may change system effectiveness, but these have not been fully examined. Therefore, this study extends the analysis to vehicle-to-vehicle interaction and context-dependent effects. To examine this gap, the experimental method is important. Field experiments can reflect a real road, but it is difficult and risky to repeatably produce the tunnel situation. A single-agent simulators are safe, but surrounding vehicles often follow predefined behavior, so real-time vehicle-to-vehicle interaction is limited. A monitor-based simulator also have limited field of view and limited reproduction of lighting or dark adaptation. For these reasons, I use a multi-agent VR-based driving simulator. This approach allows multiple drivers to interaction in real time while also providing an immersive tunnel environment. Based on this gap, my study have 3 objectives. First, I evaluate whether VMS and HUD improved the tunnel driving behavior and vehicle-to-vehicle interaction stability compared with no information. Second, I compare VMS and HUD by delivery mode. VMS is roadside fixed location system, while HUD is an in-vehicle driver-centered system. So I examine whether they produce different behavioral response pattern. Third, I analyze whether luminous and speed limit conditions change the effectiveness of each system. The hypotheses follow the same structure. Both systems are expected to improve safety. VMS HUD are expected to show different response pattern, and luminous and speed limit are expected to moderate the system effects. Now I'll move on to the methodology. The entire research process consists of 4 stages: experimental design, data collection, analyze, and conclusion. I will explain the detail of each stage in the following slide. The experimental setup was designed across 3 dimensions. First, I designed a straight 3-lane tunnel scenario. Inside the tunnel, the started vehicle was placed as an accident situation. 2 participants' vehicle and 1 experimental control vehicle drove in the same virtual environment. This allowed me to observe both individual driving behavior and vehicle-to-vehicle interaction. Second, I used 2 luminous conditions, bright and dark. The bright condition followed the tunnel lightning standard, while the dark condition represented a lower lightning situation. Third, I implemented a 2 information delivery system. VMS provide roadside warning before tunnel entry. HUD provide in-vehicle warning within the tunnel field of view, including a dynamic warning when the risk became closer. The main message context was kept similar, though the key comparison was the delivery mode. A total of 32 licensed drivers participate in this experiment. They are divided into 2 speed limit groups. Regarding sample size, 32 participants falls within the common range of driving simulator study. And the G-power sensitivity analyzed detail in the appendix confirm that this sample is sufficient to detect medium effect in the within object comparison, which are our primary analyze for information system and luminous effects. However, because the speed limit comparison used 16 participants per group, it was mainly suitable for detecting large effects, so the speed limit results should be interpreted with caution. After requirement, each participants first complete the practice drive to become familiar with the VR simulator. Then they experience 5 experimental scenario, 1 control scenario, and 4 information scenario combining VMS and HUD with bright or dark luminous. In this design, information system and luminous were treated as a within subject factor, while speed limit was treated as a between subject factor. The scenario order was randomized, and the vehicle position were counterbalanced to reduce order effects and learning bias. After the driving experiments, participants complete the questionnaire to evaluate simulator sickness and presence. These were used to check the reliability of the VR experiments. This study used 6 measurement indicators. The first group is individual driving behavior 3 indicator, and the second group is a vehicle-to-vehicle interaction of 3 indicator. This structure is important because this study does not only examine the one driver's behavior, it also examines the stability between the leading and following vehicle. For statistical analysis, I first checked the normality using the Shapiro-Wilk test. Then I used a pair t-test for information system and luminous comparison. Because these are within subject comparison, For speed limit, I use an independent sample t-test because the 80 and 100 km per hour group were different group. The significance level was set at p less than 0.05, and since these are comparison based on pre-specified hypothesis, so I didn't apply multiple comparison correction. Now I will present the result. The first, I examined the individual driving behavior. For average speed, both VMS and HUD significantly reduced the speed compared with the control condition. This means that information helped driver slow down before or during the tunnel section. For maximum deceleration, both systems also reduced harsh braking, so drivers didn't need to brake as abruptly when information was provided. For TTC, both systems significantly increased compared with the control condition. HUD showed the tendency toward longer TTC than VMS, but this difference was marginally significant. Overall, both systems improved the individual driving behavior, but the direct difference between VMS and HUD was limited for these indicators. Next, I examined the vehicle-to-vehicle interaction stability. For average speed, both VMS and HUD significantly increased the distance from the lead vehicle compared with the control condition. Importantly, VMS showed significantly larger headway than HUD. For speed deviation, both systems reduced the speed difference between the participant vehicle and the lead vehicle. For braking reaction time, both systems also reduced reaction time compared with the control condition. These results show that the safety benefits were not limited to individual driver behavior. They also extend to the interaction between vehicles. This slide compares the response pattern of VMS and HUD. This does not mean that one system is clearly better than the other. Rather, the two systems showed similar overall safety effects, but some indicators suggest a different response pattern. VMS was provided from the roadside before tunnel entry, so driver had more distance to adjust their speed and maintain a larger headway. It was provided inside the vehicle and include a dynamic warning based on driving risk, so it may be have supported more immediately response and longer TTC. Therefore, VMS may be more related on spatial safety margin, while HUD may be more related on temporal safety margin. Next, I examined the moderating effects of luminance. For VMS, most indicators didn't show clear difference between bright and dark condition. Only TTC increased in the dark condition. For HUD, the pattern was different. HUD was more sensitive to luminance condition, especially in vehicle-to-vehicle interaction indicator. In dark condition, HUD user maintain a larger headway. However, speed deviation and brake reaction time also increased. So these results need careful interpretation. A larger headway is positive, but higher speed variation and slower braking suggests increased information processing burden. Therefore, the luminous part of hypothesis 3 was partially supported. Finally, I examined the moderating of the speed limit. Overall, the 80 km per hour condition showed safer pattern in selected indicator. For VMS, maximum deceleration became softer at 80 km per hour. Brake reaction time also became shorter. For HUD, average speed was lower, maximum deceleration became softer, and average headway increased at 80 km per hour. So the lower speed limit strengthened safety-related effects, but not in all indicators. The affected indicators were different between VMS and HUD. Therefore, the speed limit part of hypothesis 3 was partial supported. So now I will move to the conclusion. The key finding can be summarized into 4 points. First, both VMS and HUD improved the tunnel driving safety. Drivers drove more slowly, braked less abruptly, and maintained a longer TTC. Second, the benefit extended to vehicle-to-vehicle interaction stability. Both systems increased the headway, reduced the speed deviation, and shortened brake reaction time. Both systems increased the headway, reduced the speed deviation, and shortened brake reaction time. Third, the VMS and HUD showed a different reaction pattern in some indicator. VMS was more related to a larger spatial margin, while HUD was more related to a longer temporal margin. Fourth, the effects depending on the tunnel condition. HUD was more sensitive to luminance, especially in V2V indicator. Also, the 80 km per hour condition showed a safer response in selected indicator. Overall, this finding suggests that tunnel information delivery system should be designed in a context-aware way, not as a one-size-fits-all solution. Nevertheless, this study has 3 main limitations. The first, sample size and participant diversity were limited. This study includes 32 participants, and most of them are relatively a younger driver recruited from the university. Although the G-power sensitivity analysis showed a sufficient power for the main within subject comparison, the between group speed limit analysis was mainly sensitive to large effects. Therefore, future studies should recruit a larger and more diverse sample, including different age group and driving experience level. Second, the experiments used a single straight tunnel scenario, but real tunnel can have different geometry, lengths, and traffic volume and accident type. So future study should test VMS and HUD in more diverse tunnel type and traffic environments. Third is that this study used a VR-based simulator. VR allows safe and control experiments, but it cannot fully reproduce a real-world driving condition. Therefore, future work should validate this finding using a real tunnel data. For example, on-road observation or from the instruments vehicle study. Through this future study, we can develop the more practical guideline for designing and operating information delivery system in tunnel. This concludes my presentation. Thank you for listening.